Okay, everyone, this is the second video for your BAM assignment, and this is actually going to help get you into the B part. So in the B assignment, we are going to acknowledge the fact that, this acceleration here of 9.8 or negative 9.8 meters per second squared for the whole launch of a rocket isn't really a good estimate. As we get further and further away from Earth, the acceleration actually changes. So what I'm going to do is, and you don't need to do this in your version, but in my version, I'm going to have a new column here, and I'm going to call it actual acceleration. Let's do actual accel to keep it short. And we're going to figure out what the actual acceleration should be. Now, based on some of the physics problems that we've done in class, you should know that I'm just going to use this space to type. Fg is equal to g times m divided by r squared. So we want to somehow capture this formula in here, except we want an acceleration out of gravity. Well, we also know that Fg is equal to mass times acceleration. So if that's the case, I can divide this formula by m and divide this formula by m, and I end up getting this. A is equal to g m over r squared. So now if we can somehow figure out a way to write this formula in Excel, we'll be good. So I'm going to take this and just move it over a spot so we can have it as a reference, and I'm going to write equal sign here. Equals g. Well, I don't have anything on my spreadsheet right now that represents g, so that's going to be a problem. I could type the number in. The number is 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. But putting that number in here makes this formula awful messy. And I always tell you guys when we're doing physics to only work with variables, not to work with numbers. The same applies in Excel. So instead of typing this number here, I'm going to take this, cut it, and I'm going to paste it somewhere out of the way, right here. Now, I just pasted it, and you might say, hey, it's coming up as 0, but if I click on the cell, it's still there, and if I just kind of one-time click it and look up in this kind of shortcut box, it's still there. The reason it's showing me as 0 is because right now this box is formatted in a way that it's just trying to give me normal numbers, and 10 to the minus 11th is not a normal number. It's an extraordinarily small number, so it approximates it to 0. I can change that by formatting this box differently. Instead of it being an automatic format, I'm going to say force it to be a scientific format. So now that looks more along the lines of what I want. So here's the point where I'm going to caution you, or give you a little bit of caution about just throwing random numbers in Excel or in Sheets, because this number floating up here is kind of confusing. So let's give it a label. I'm going to write big G here. Actually, let's write G equals. And I'm even going to align this to the right. And then on this column, I'm going to write the units, which is meters cubed per kilogram second squared. So now, E2 is the value for G. Well, I have other things in this formula that I need. For instance, M. So this formula says A, or acceleration due to gravity, is a product of G times mass divided by R squared. Well, the M it's talking about here is the mass of the planet. In this case, Earth. But I'm going to write M planet here equals, and for Earth it is 5.97, equals 5.97 times 10 to the 24th kilograms. And let's align this guy to the right and this guy to the left because I'm a little obsessive compulsive. And now that looks pretty. So now we have the mass of the planet in there. The last thing we have is R. Now, when we've discussed problems in class, we've said that R just means the radius of the planet. But that's no longer the case. And here's why. in this problem, we're talking about a rocket leaving the planet. So if we picture the planet as, imagine it's this blue block over here. Here's Earth. Typically, nothing on Earth ever goes really high. It might be a little smidgen, a pixel or two above this blue line. But satellites in orbit might be all the way up here. So if I have this red block represents a satellite in orbit, or where our rocket is going to go, well, the distance from this block to the center of the blue block is significantly more than just the radius of the blue block. It's much higher. So in this case, we could say r is equal to two things. It's equal to the radius of the planet, our planet, and the current altitude. So I need to capture that in this formula. Now we can do it one of two ways. We can make a new column right here where I put r, or I can just embed it in the formula. I'll let you decide how you want to do it, but I'm just going to put it right in the formula because I don't think this is especially or too messy. In the meantime, though, let's get the radius of the planet up here. So r planet, and I apologize that I'm using a capital R. Well, let's make it a lowercase r. But I can't do my subscripts in Google Sheets. Otherwise, I would just do r subscript planet, but it's hard to do that here. So the radius of Earth is 6.371. Whoops. Equals 6.371 times 10 to the 6th meters. Oh, no, meters. There we go. All right, and let's format this to be scientific too, just so that we're consistent. Okay, so now that we have these three values, let's go and write this formula. Remind you, here's the formula again. A equals g times m divided by r squared, where r is radius of the planet and the altitude. So we're going to write a formula in. The first thing we do is hit equals. Now we need to put g in there. Well, g is this value, the value located in E3. So you can type E2, or you can click on E2, or you could do my favorite, which is just to use your arrow keys, and you can kind of tab up to it. So equals, boom, 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 I'm just walking up, E2. So it's A is equal to G times mass of the planet, that's E3, divided by r squared. Now remember, in this case, r is two things. It's the radius of the planet plus the current altitude, which is over here in B7, and it's that whole quantity squared. So there we go. Here's that formula. A equals G times M divided by R squared. G times M divided by R squared. Enter. And what do you know? Let's format this to be a normal number. Oops. What do you know? But the answer I get when we put this calculation in is 9.81. So when my altitude is 0, the actual acceleration is negative 9.81 meters per second squared. Oh, you know what? To make this work, let's throw a negative up front too, just so we don't confuse ourselves. Negative 9.81 meters per second squared. So there's not really any difference here. I mean, I can make this a negative 9.81 too and change all that. So what happens as we drag this formula down? Let's see. So I'm going to drag it down a little bit, and oh my goodness, I blew everything up. So we have a problem, obviously. Let's figure out what it is. Now, these cells that say hashtag value are giving you errors and saying you can't add, but actual is a text and cannot be coerced, so it's saying you can't add to text. So let's figure out what it's doing. Here we got a number. It's crazy, but let's take a look what the formula says. E3 times E4, right? Or you can double click in here. E3 times E4 divided by E5, well, that's not what we want, plus B8, well, that's what we want. So the problem that we have here is that's no longer referring to G, and the reason for that is because G doesn't change, so it should be an absolute reference. once we drug that formula down one, it assumed that all the other information went down one cell. So you can see these three boxes up here that we used all shifted down by one. So let's go back to our original cell and make the things that need to be absolute values, or absolute references. So E2, G, that doesn't change, so let's put our dollar signs in. Now it's an absolute reference. Mass of the planet, that doesn't change, so it should be an absolute reference. Oops. E4, the radius of the planet doesn't change, so it should be an absolute reference. B7, the altitude does change. So since the altitude does change, we can just leave it as it is, B7. Now, it didn't affect anything here, but watch as we drag this formula down. Skabam. And you notice, even 1, 2, 3, 4, 5, 6 seconds into the trip, you already start to notice that the acceleration is changing. Not a lot, negative 9.81 to negative 9.77, but it is changing. If we take this down even further, say to 120 seconds, now we're 2 minutes into the trip, the acceleration has changed quite a bit. Negative 9.31. If we go down further, uh-oh. Now we end up hitting a peak somewhere because our velocity changed, but we get down to about negative 9.2. If we were to go back all the way to the top and change our initial velocity, let's say to 11,200 meters per second, which is really fast. It still changes kind of slightly up here, but take a look as we go down. The acceleration drops dramatically. After only about 3 minutes, the acceleration due to gravity is down to about 5 instead of 9.8, which we're used to. So this does have a big effect. Our assumption that acceleration of gravity is negative 9.81 all the time is good when we're near Earth's surface, but as soon as we start getting high up into the atmosphere, that goes out the window and we can't use it. Alright, before I go, I'm going to get rid of these pictures over here. I'm going to get rid of these two formulas, and here is where we'll pick up for the next problem. Oh, we should do one more thing. Right now our velocity is still being calculated using acceleration, but we want it to calculate using our actual acceleration. So instead of going to D7, we should be going to E7. Oh, I'm blowing up as I do physics. There we go. And we can drag that formula down and we're all set. Alright. See you in a little bit.